Hi, in this video we are going to talk about window sliding technique. Before we talk about the technique, let's understand this problem. Let's try to solve this problem and we'll understand the technique with this example problem. So the problem is we are given an array of integers and we are given a number k. Our task is to find out maximum sum of k consecutive elements in the given array. For example, if you are given this array and k is 3, you need to consider every window of size 3 or every subarray of size 3 in the given array, and you need to find sum of every subarray and find the maximum of all these. So this subarray has size sum 39, this subarray has sum 33, right? This has sum as 45 and this has sum as 22. So this is the maximum sum, that's why our output is 45. If k is 2 in this array, then 96 is the output. Now please pause this video and try to write down a function that takes an array as an input and the number k as input and returns the maximum sum of a subarray of size k. Let us first talk about a naive solution to solve the problem. The idea is simple. We begin with this index, we count the sum of first k elements, then we come to this index and find the sum of k elements beginning with this index, then we come to this index, find the sum of k elements, and we keep track of the maximum sum so far. Right? And if the current sum is more than the maximum sum or result, we update our result or maximum sum. So that's the simple implementation of the idea. We initialize our result as minus infinite, which is integer.min in C++ and integer.min value in Java. Then we consider every index I as a starting point. See, we are going to consider I as a starting point and then we are going to consider k elements after it. So the valid ending index should be smaller than n, right? That's why we run this loop I equal to 0 and I plus k minus 1 should be smaller than n and I plus plus. Now inside this loop, we compute the sum that has k elements and these k elements begin with index array I. So we run a loop k times and inside this loop, we add arri plus j, right? Elements beginning with index I and then k elements. So j is shift here. And if this current sum is greater than the maximum sum or result, then we update the result. And at the end, we simply return the result. Now, what is the time complexity of this? See, the time complexity is clearly, this is big O of n loop and this is big O of k loop. So you can say it's big O of n into k and auxiliary space is big O of 1. Now, please pause this video and try to think of a solution that works in linear time. Let us now talk about window sliding technique. The idea of this technique is compute the sum of current window or subarray using the sum of previous window. What we were doing in the naive approach, we were first computing this sum, then we were computing this sum, then we were computing this sum. See, we are going to do the same thing here, but when we come from here to here after the first slide, we are not going to run a loop k times to sum these k elements. We are going to use the sum already computed, which is 34. And from the sum, we are going to get the sum in big O of 1 time rather than theta k time. How do we do it? When we come from here to here, we know that the first item of the previous window should be removed and the last item of current window should be added. So we subtract 1 from it and we add 20 to it, right? Given starting and ending indexes of current window, we can figure out what was the first element of the previous window and what is the last element of the current window. We can easily figure out the last index of the current window is the last element, and by doing some computations using k, we can figure out what was the first element of the previous window, and that way we can compute the sum of current window in big O of 1 time. And same thing we do when we do slide more. What we do in the second slide, we want to compute the sum of this window. We subtract the first element of the previous window, which is 8, and we add the last element of current window, which is 7, right? So we subtract 8 and add 7. So we get 52, which is not more than current result. So we keep the result as 53. Our output is going to be 53 here. So the idea of window sliding is if you can do the required computations for current subarray, using the computations done for the previous subarray in big O of 1 time or in less time, less than the linear time, then you use sliding window. It is sum here, but it can be anything. It can be XOR of the numbers, product of the numbers, or anything which can be done in big O of 1 time or less than linear time. See, instead of doing a sum by running a loop, what we did, we subtracted the first item of previous window, added the last item of the current window. If it is XOR, you can again do the same thing. You can XOR with the first item of the previous window. They'll nullify each other. First, the first item will be removed and you can again XOR with the current, the last item of the current window. This way you can also find out maximum XOR, and you can do the product problem also same way. You can divide the first element of the previous window and you can multiply the last element of the current window, right? So there can be multiple problems where you can do computations for the current window using the computations done for the previous window in less than linear time. So that's the idea of window sliding. Now you have complete idea about the approach. Please pause this video and try to write down the complete implementation of this maximum sum problem. Here is the implementation of sliding window technique. We take array as an argument, size of the array as another argument, and k as third argument. So what we do, we initialize the current sum as 0. We run a loop, we compute the sum of first k items, right? And we also initialize this as result, right? We want to find the maximum value of current sum. Now for remaining windows after the first window, you can notice that there is no loop inside it, right? What are we doing? We are considering I as the ending point of current window, right? So I is initialized as 4 here, and you can notice that this is the ending point of second window, right? When I is 4, we are running for the second window. We have already computed sum of the first window in the first loop, right? Now in the second loop, we compute the sum of this window using the sum of previous window. And then in the next iteration, the second iteration of this loop, we compute the sum of this window using the sum of previous window, right? So what are we doing inside this loop? We are adding ARRI, last item of the current window. See, there are two different types of programmers, and as a programmer, you might have implemented in a way where I is the first element of current window. You might have begin I with 1. That's also fine. You can implement it both ways. The implementation here that I have done here, I have considered I as the last index of the current window, right? That's what I is. So when you run for the first iteration is the last index of this window, right? And how do we compute the sum of this window? We add the last item of the current window and we remove the first item of current window. So when I is 4, the first item is going to be I minus k, 4 minus 4, 0, right? So we remove ARR 0, which is 1. So that's how we get this sum 53. Then we compare if it is more than result. If it is actually more than result. So we update result to 53. Now we begin the second iteration. And in the second iteration, we compute the sum of this window. So what we do, we add 7 and we subtract 30. So what is I now? I is 5 now. So 7 is at index 5. And this element 8 as at index 1. 5 minus 4, 1. Right? And the current sum turns out to be 52, which is less than result, so we don't update the result. Now if you take a closer look at this implementation, it's clearly theta n. We are running a loop k times and then we are running a loop n minus k times. So it's clearly theta n and auxiliary space is big O of 1. So this was our first example of window sliding. We are going to do many more examples of window sliding in the upcoming videos.